Hey, good people. Welcome back to Unit 8, Day 2, Part 2. Today we talked about springs, and now we're going to do a little bit of a practice problem here together. This practice problem comes from page 371, number 1, Part A in your textbook. It says, I have my book right here. You have your book right in front of you so that you can read along with us. It says, suppose the spring in sample problem A is replaced with a spring that stretches 36 centimeters from its equilibrium position. What is the spring constant in this case? Well, in order to answer that question, we're going to have to look back at sample problem A. So move your eyes or your nose slightly to the left where you will see page 370, and at the top of page 370, sample problem A says, if a mass of 0.55 kilograms is attached to a vertical spring that then stretches the spring 2.0 centimeters from its original equilibrium position, what is the spring constant? Here's the idea. When it comes to springs, every spring has its very, very own unique spring constant. And the only way to find out what that spring constant is to look for it experimentally. Here's an experiment that you can use to figure out the spring constant of a spring. Take a spring, just like this one. Have it in its nice, unstretched equilibrium position. Then, add a bunch of mass onto the end. Whoa, here's some more mass here. Here's some more mass here. Add a bunch of mass onto the end. If you add mass, that spring is going to stretch under the weight of the new load. Here's the idea. The idea is if you can measure how much this spring stretches by, if you can measure this stretch and you know how much mass you put on the end, you can figure out how stretchy or how stiff this spring is. You can find the spring constant based on how far it stretches from its equilibrium position when you put mass on the end. That's the idea. We're going to actually start this problem by doing a free body diagram of the mass on the end here. So let's draw a picture together. We're going to draw a free body diagram of the mass when it is stretching the spring and is being held up by the spring. Wow, string twice. Craziness. Here's what it looks like. You have the mass on the end. The mass is being pulled down by its weight. That's gravity. But the mass isn't plummeting down towards the center of the earth because the spring is helping to hold it up. This is the spring force that is counteracting the force of gravity. In this case, I always like to ask students right here, which arrow should we draw bigger, the weight or the spring force? Correct answer? Same. You should draw them the same length because they are going to balance each other out so that this mass here isn't moving. Now, let's write a net force equation. The net force that's acting on this mass is equal to the force from the spring plus the force from gravity. Now, don't forget, whenever you draw a free body diagram, it's essential that you define your axes. I'm going to call, in this case, up positive y. So, now, when I rewrite this equation, I'm going to rewrite it as positive. I'm getting rid of the vector hats because I'm replacing the vector hats with positive and negative signs. The positive force of the spring, because it's going up, minus the weight, because it's going down. Notice, because this thing is at rest, it's not accelerating. The net force is going to equal 0 according to Newton's second law that F net equals ma. Since A is 0, F net is 0. So we can set this equal to 0 here. Now rearrange and we get that the spring force is equal to Fg. Hey, do we know an equation for Fg? For sure! We've had it in our back pocket since first semester. Fg equals mg. Do we know an equation for the spring force? For sure, we learned it today. We know that the spring force is equal to K delta X, like so. Now some people might be panicking here because I did not put a little negative sign there, and you know what? I'm not going to put a little negative sign there. And they say, but why, Miss Wilson? You said today in class that the equation for the spring force is equal to negative K delta X. Here's why I'm not going to put the negative there. Do you remember us talking about how that negative was a directional thing that took care of direction? Well, check it out. I already took care of direction here. I already said that the spring force is in the opposite direction of the way that gravity is pulling on the mass. So gravity is pulling the mass down, the displacement is down, but the spring force is acting up. So I have already taken care of direction here, and I do not need a negative sign anymore because I took care of the direction myself. Is this track with everybody? Let's rearrange to solve for K. K equals mg over delta x. At this point, you could easily plug in numbers and get to a final answer. That's all for today, folks. I hope you have a wonderful, wonderful rest of your day, and I'll see you later. Bye, good people.